Good afternoon. Good afternoon. It's a special pleasure and honor to introduce Drazen Prelec. Drazen Prelec is a professor in the Department of Brain and Cognitive Sciences, the Department of Sonomics, and the Sloan School at the Massachusetts Institute of Technology. He started as a mathematician, receiving his bachelor's degree in applied mathematics from Harvard in 1978, and then moved to psychology. It gets more interesting. Receiving his PhD in experimental psychology in 1983, also from Harvard University. Drazen works both on the development of normative decision theory and on the exploration of empirical failures of that theory using behavioral and neuroscience methods. He made many important contributions in different fields of behavioral economics, and working on starting on something that is close to my heart, the matching law, the matching behavior. This was with Richard Bernstein, and made contribution to the field of temporal discounting. This is with George Lowenstein. Many people ask me whether George Lowenstein is a relative of mine. Unfortunately, the answer is no. He worked on probability weighting. More recent projects have focused on non-causal and diagnostic motivation for actions. I think he will tell us more about it on Thursday. And on game theoretic mechanisms for eliciting and combining information from individuals when ground truth is non-verifiable. I guess it will be related to today's talk. Drazen's work, while dealing with the most fundamental questions in human behavior and motivation, are also amusing and fun. A few examples here in Dan Ariely's book on rationality and irrationality. His papers, I'll quote the paper, Man Search for Meaning, the case of Legos. This is together with Dan Ariely and work on Tom Sawyer and the construction of value. This is with Dan Ariely and George Lowenstein. Drazen's work has been recognized by numerous fellowships in the world, including those from John Simon Guggenheim Foundation and the Harvard Society of Fellows. Without further ado, Drazen Prelec.
Thank you, Jonathan. I want to thank Elon also for the invitation. Is it okay if I don't have can you hear me like this?
Yes, but it's not well recorded.
So you want to make sure that I'm plugged in. It's okay. So I have to say this invitation reflects the breadth of your interest, because I will not talk about neuroscience, even though the subject matter is full of pregnant with potential for speculating wildly and irresponsibly about how this might have some role to play in neuroscience. So the word neuroscience will not be mentioned for the next 60 minutes, but perhaps maybe picked up over the next days. It's a special pleasure to be in Jerusalem, and it gives me an occasion to reflect on the influence that the Israeli scholars have had on my career and my interests. Last time I was here was in 1995, and it was I had a chance to speak for the last time with Amos Tversky, whose influence on all of us is extraordinary. So where was I? Yes, I had mentioned Amos Tversky, who's been extraordinarily influential, and also the Center for Rationality, which is here in Jerusalem, and which may be unique, and which has developed a style of psychological exploration, investigation based on using rationality to uncover irrationality. And that is, I would say, kind of a dialectical approach to understanding the mind, where you use a theory to tell you what you don't understand, basically. The other person whom I haven't met, really, except briefly, but was important for this talk, is Robert Aumann, game theorist, received a Nobel Prize some years back, who developed the notion of a correlated equilibrium in game theory. And that was important to me as a PhD student, and that got me started as thinking of it as a technical device for solving the problems we'll discuss today. So in this talk, just to give you an outline of the different parts, I'm going to describe a problem, the verifiability problem, then a specific solution, not that I have developed, which was at a colleague's suggestion labeled the Bayesian truth serum, and then going a little bit backwards, explain the theoretical assumptions that make this solution work, and then some necessary mathematics for how it does work, and that would be roughly 30 to 40 minutes. And then in the end, I will discuss experimental practical applications. So first, to define the problem. And here, I would like actually to create a little, in this room, a little non-verifiability, collected non-verifiability situation. So what I have here is a bag with colored chips. I'm pretending that I don't know the different colors of the chips. And I would like everyone to do the following. Reach into the bag, take out one chip, but make sure nobody else sees it. Note the color, and then drop it back in and pass it to the person next to you. So as we talk in the next few minutes, everyone will have a little non-verifiable experience, which is your private secret note of the color. And the stance that I'm adopting is I don't know what the colors are in there. I don't know what the mixture is. Later on, I will assume that you do know what the possibilities are. There might have been a different bag. I actually don't know what's in that bag, literally here. Okay, so this can go around while we talk. Now, what is the non-verifiability problem? It's usefully defined by two lists. What you see on the list are domains where there is a objectively correct answer that can be verified in a public forum. And these are lists such as generally forecasts, business forecasts, sports forecasts, economic forecasts, the outcomes of litigation, weather, and some, but not all, scientific predictions. When I say not all, some scientific predictions, like in string theory or evolution and astrophysics, may not be verifiable in practice. And on the right side, you have a completely different list. These are concerns, domains, areas of exploration, contention, discussion, where the subject matter and opinions are not verifiable. Legal disputes, historical interpretation, forecasts into the very remote future, so it's not practical to verify anything, psychiatric diagnosis, artistic judgments, thesis of philosophy, and even whether Bayesianism is correct, let's say. It's not a verifiable proposition. So when you look at these two lists, my own reaction is that the list on the right is much more interesting than the list on the left. Much more interesting to think about. But it sort of belongs in the basement from the standpoint of scientific respectability, because there's two problems with the list on the right. Generally, when people make opinions there, you don't know if what they're saying is expressed honestly or is motivated by some conscious or unconscious desire to affirm a point of view or to exploit something. And then you also don't know which category, whether when there is a disagreement, what is the right answer. And that has made discussion in those domains scientifically not a part of science, genuine science. It is a part of culture. One example I don't have on the list is counterfactual discussions. What would have happened if? They are a part of law. You can't settle litigation without proving to a jury this would have happened had that been done. But if you try to publish a paper that hinges on a counterfactual in a scientific journal, and I have had this experience, the referee will say, this is speculation, it doesn't belong in science. So the fact that the area on the right, and one psychological observation is, when our mind is involved with the list on the right, it doesn't seem to be doing anything fundamentally different than when it's dealing with issues on the left. So it's not a psychological difference from the standpoint of someone who reasons about these things. It's really a difference from the community's perspective. Can they prove something right or wrong? I would say it even affects research, and I wouldn't say neuroscience, but let me do it. Suppose I ask Jonathan what was the color that you observed? Brownish. Okay. I'm not quite sure. Brownish. Now, let's say that Jonathan said this in an fMRI machine, and I observed the recording of his brain. Now, what would I report? Well, there's two ways to treat the situation. This is not philosophy of science. One way is to think is that there are two people giving reports. I'm reporting what I see on the brain image, as you are stating that you see it orangish. And the second person providing a report is Jonathan, who's saying it's brownish. And we're both reporting something. You're reporting a phenomenal experience. I'm reporting what I see. The other way to say it is that if the only person who's doing any reporting is me. I'm reporting what I see on the fMRI scanner, and I'm also reporting a piece of behavior by Jonathan, which is that he has expressed the word, I see a brownish color. And that's science, because that's verifiable. Other people can peek over my shoulder and say, yes, you did observe this. Yes, Jonathan did say this. If we take the first stance that Jonathan is directly has a status of an observer, we cannot check whether it's really brownish or something else. And this is a real problem when a patient says, this pain feels like 3 on a scale of 1 to 10. What does 3 mean? That's that. So I have to say, just personally, my own interest in this was based on how can we have criteria for phenomenological descriptions? Are they just chat, or can they have a status of an actual report of some event? That's the. Okay. This is an example of. We're going to see art at the end of the talk, but let me just continue now. Interesting application, of course, is art. This is non-verifiable. Which of these is more valuable intrinsically? What is verifiable, of course, is the market value of a piece of art. So if you were surprised by this, as I was, that the one on the right is worth 2 million, the one on the left is worth 50. So generally, when we test any method that can deal with non-verifiable content, we can only test it on verifiable questions. But our interest really is in non-verifiable things. Okay, so now I forgot to say one thing here. The fact that the discussion with respect to non-verifiable domains, we don't have standards for honesty, we don't have standards for objective truth, has two negative consequences, cultural consequences. The first one I already mentioned, that people tend to think of that this discussion is arbitrary, that anything goes, anything that people say is an opinion. The second negative and incorrect assumption is that when we are forced to somehow combine different opinions about non-verifiable questions, we tend to assume that the average opinion is correct. So if you have awards like the Oscars or things like that, judgments of, is this painting actually important, we tend to think of the average opinion as being the best that the community can achieve. And theoretically, that's a dangerous assumption, because in many cases, the information is actually buried in a small subset of individuals. So that's two things. Now, what I'm going to describe is a way that one can impose some discipline and structure on people's reports that are intrinsically non-verifiable. And by that I mean that we can give each person a score, an index, instruct them to maximize that index, and they will believe, if they conform to the assumptions of our theory, that in order to to maximize the score, they should give their honest answer, honest report of their private information, private signal. The scoring system is in the ugly-looking equation below. It actually conceals a remarkable simplicity. It's not there, and I will explain the terms in a few slides. It's a score that an individual gets in a game, and the game is analyzing the assumption that every player is a rational Bayesian individual. So this is the heavy assumption that's invoked of ideal individuals, ideal respondents that can do all the calculations required by Bayesian updating. Individuals are asked a question, they submit answers, and the novelty is that they also predict how other people will answer. So there's a secondary input that people provide, which is a prediction of how other people will answer. Both answers and predictions are scored, and the scores encourage honesty, and in cases where expertise is also relevant, the scores rank players by local expertise. And local expertise is defined as the probability they assign on the total amount of information in the group. So this is the statement of the claims. So I'm going to introduce this scoring system from the perspective of a subject, as if you were the subject in the experiment, and then I will explain the scoring system and then discuss conditions under which it actually delivers the theoretical results. So the scoring system works with a multiple choice question. It can be almost anything, and it can have any number of possible answers. So these are very simple questions. Most of the time we'll be thinking with very elementary questions. These are easy to think about, but ultimately we're interested in more ambitious things. Questions 1 and 2 deal with personal matters, your preference between wine. And question 2 is something about your habits over the last year. Questions 3 and 4 have an additional feature in that in 3 and 4 there's also an objectively correct answer. So these are personal questions, and these are questions where, additionally, we're not just asking for your opinion. We are also interested in somehow combining those opinions and coming up with the truth. Now, the question of honesty is relevant to all 4, but the question of objective truth is only relevant to 3 and 4, items 3 and 4. So if you're a person who's participating in a survey of this kind, you would see a question, you would pick an answer that's right for you, and we need some notation for the moment, and you would pick answer K, where K indexes 1 through n possible answers, and it would have value 1 for the answer that you selected, and then additionally you would give a probability distribution over those answers, which is your estimate of how everyone else in the room voted. So this is the secondary critical piece of information. Everybody provides both pieces of information, this and this. Here's an example from an actual survey. This was done in a context of predicting. This is actually a verifiable question. The context was predicting events in foreign countries. Question was, will Russia maintain any military presence in the Tartus naval base in Syria? The first thing a respondent had to predict is whether they believe this will happen or not by a certain date. Then they gave their confidence, which we ignore for the moment. And then they predicted, this is the secondary input, please estimate the likely distribution of opinions among your colleagues on a scale of 1, 0 through 10, which is, will your colleagues go one way or the other? So this is the type of input that you would provide. Everybody provides this dual input for each question, answer and a prediction. And then everybody gets a score. The score is determined by 2 statistics. The first statistics, the x bar k, is the actual distribution of votes for each question. So x bar k is how many people voted for an answer. And y bar k is the geometric average of the predicted distribution of votes. And it's geometric because behind this, the results really all rely on information theory and entropy which is not evident yet at this point. So X bar is the predicted percent who vote for an answer, X bar is the actual, Y bar is the predicted. And that difference is critical for everything in the rest of this talk. The score that you get actually is a score for both your answer and your prediction, and we can unpack it into two pieces. If you made a prediction Y1 through Ym, then the piece of your score that evaluates that prediction is what is known as the KL divergence, or relative entropy, between your predicted distribution and the actual distribution of votes. So if you're perfect, that score is 0. To the extent that your prediction is incorrect, the score drops down, becomes negative. That part is easy. It's in your interest to make the best effort and guess correctly what the prediction will be. The new bit is how you scored for your personal answer, whether you like red or white wine. That's a personal answer. Nobody knows. Yet on claiming, you have to tell the truth if you want to maximize your score. So how is that possible? The score that you get for your personal answer is this first part here, the information score, and that plucks out the answer that you endorsed, calculates how many people picked that answer, divides it by the predicted percent that would pick that answer, and takes the log. So it gives credit for an answer that exceeds expectations, punishes an answer that falls short of expectations. It's like picking a stock. If you pick a stock that does better than people think at the time, you do well. If you pick a stock that does less than people think at the time, you do poorly. And the claim is that since you don't know what that ratio is, you don't know how many people will pick that answer, you also don't know what the predictions will be. The claim is that under certain assumptions, if everybody's rational, you cannot game the system. You must give your honest opinion. That's the claim. So that claim, now I'm going to state it in words. There are sort of two claims in the background. One is you should always expect, if you're a Bayesian, everybody else is a Bayesian, that your honest answer will be surprisingly common, that you should always expect that your answer will prove to be more popular than people think it will be. And that's true for everybody. And that happens to be true, empirically and theoretically, sort of a gratifying thing. The other issue is when truth is impersonal, where there is an objectively correct answer, the answer whose popularity exceeds expectation should be the correct answer. And that's a claim we'll get to in the second half of the talk. So, I'm going to skip the notation here in the interest of time and give you an intuitive argument. Intuitive argument, now we're mapping up, has everyone seen seen a color? Everyone drew a color? Okay. So what do we think? We think of these colors as phenomenal observations. That is, as if you are at a wine tasting and you've tasted a wine, you've had an experience, nobody knows what that experience is. Here you observe the color, you put the little chip back in the bag, it's gone, nobody has observed it, it's only in your memory. And we're going to assume now for a moment a fantasy land of perfect Bayesians. Perfect Bayesians meaning that we can do all the Bayesian updating that is necessary in this situation. So, now what that means is that if you have some idea about what the distribution of colors might be in the bag, once you've drawn a color out of the bag, that should change your prior beliefs to posterior beliefs. And you do that calculation using Bayes' rule. That's easy mathematically, but quite slippery psychologically. And I have to say, I once, in a very smart group of MIT undergraduates, I said, let's suppose I show you a bag, unknown colors, black and white. And you make an estimate of what percent are going to be black. And I reach in and I pull one out, and it's black. And I said, well, how will this change your estimate about the mixture? And what I thought was the smartest student in the room said, well, there's going to be more white. And I said, why? Well, because there's one less. You've taken out a black one, and therefore there must be one less. Whatever I thought before. And I thought to myself, that's the first time I heard that answer, but that is not the right answer, by the way. But it was good for MIT. Okay, so let's go back to wine. Do you like red or white wine? That's a personal question. If you run this, what do you observe? You ask people to predict how many other people like white. So these are typical, this is real data, but not human subjects, IRB approved. Estimates by people who personally like white of how many people like white. You see numbers are generally above 50. And then if you ask people who personally like red, they'll give numbers that are lower. And if this wasn't true, this talk would not be given empirically. Turns out this is empirically true. It means that people are directionally Bayesian, even if we don't have little wheels, Bayesian wheels spinning in their head. Directionally, their judgments conform to Bayes' rule. So why, now the next claim is, suppose you personally like white, why should you be honest in this game that I've set up? I'm arguing that you should expect, or let's say red, the popularity of red will be underestimated if you like red. Here's the argument. This is the easy argument, intuitive argument. You like red wine, okay? This is the population. And you are making an estimate that this fraction of the population personally likes red. Well, and now you're put in this game where you have to give an answer that you think is going to be underestimated by the other people in the room. Well, the people who like red will give estimates like this. Now, what about somebody who likes white? Well, that person is going to estimate a smaller proportion liking red by Bayesian updating. And when the dust settles, when we average all the predictions made by all the people in the room, the average prediction is going to be somewhere between your prediction and that person's prediction. But you believe that your prediction is the right one. And therefore, you must believe that it will exceed expectations. That's the argument. It's an argument that since you believe that your prediction is correct, other people will give a different prediction because they have different information. Therefore, they're incorrect. Therefore, you believe that the popularity of your honest opinion will be underestimated. That's a true fact mathematically, and it's true more or less empirically. I think it's kind of stunning, actually. Not totally intuitive. And the beauty of it, it doesn't depend on whether you think, the argument doesn't hinge on whether you have an opinion that's general or opinion that's specific. So for example, if you think your opinion is very unusual, the argument still is valid. You think it's going to be less unusual than people think. So you should always expect truth to be underestimated. And it sounds paradoxical because it's true for everybody. That's what gives it a paradoxical flavor. That's the easy part for n equals 2 colors. What if we have 3 colors? Now these are the balls in the urn. Has anyone drawn a brownish, Jonathan has. You've drawn a brownish yellowish ball, right? Suppose I told you there are 2 possible urns that we drew from. And it's true, there were 2. Either this one or this one. I don't know which one it was. Now you drew yellow. What do you think is the most common color that people drew in the room?
Yeah, yellow. I drew yellow.
No, these are the distributions. Think again. I'm either drawing from this one, or I'm drawing from this one, 50-50.
But you didn't say which color.
Okay, those are the colors. Those are the actual colors. And if you drew red, then there's magic. Somehow red here. Those are the actual colors. And if you drew yellow, what do you think the other people will draw? Most likely. Blue. Because yellow says 2-to-1 odds, it's here, there's blue. And now, is it true? How many drew blue? I think how many drew green? Okay, so we're actually drawing from this one. All right, too bad.
Colors
All right.
are not friendly to colors.
No, okay, all right. All right. So, now, why am I doing this? Suppose you draw yellow, you think other people are observing blue. Why should you believe my theoretical claim that to maximize that log ratio, you have to tell the truth? We're going to just prove it by computation. Before you drew a color, your prior should have been 40% blue, 15% yellow, 45% green. This is just averaging both urns. After you drew yellow, posterior on blue goes up to 0.5, posterior on yellow goes up to 0.17, posterior on green drops to 0.33. Now we compute, so the posterior moves for blue. Now we compute the log of this, the expectation of the log of that ratio, and calculate the score that you would get. And the score that you would get for telling the truth is positive 0.03 for lying and saying you observed blue. It's minus 0.06 for lying and saying you observed green. It's minus 0.48. So if you observe yellow, your score is always maximized by saying yellow, no matter how many colors, no matter how many urns. That is the honesty theorem right there. What does it rest on? And I think in the interest of, I will give you very, very quickly what I think is the heart of the mathematical argument. The heart of the argument involves the fact that when you're drawing these balls from an urn, your observations are conditionally dependent on the distribution of different colors in the urn. So X bar is the actual distribution, and these down there are individual different observations. And now let's focus on just 3 of these. X bar is the actual composition of the urn. X2 is somebody else's prediction of X1 is X1 is Jonathan here. And now Jonathan is thinking he's going to be predicted by someone who's seen the composition in the urn, who will estimate a probability that he has observed yellow, which is equal to the actual frequency there. And he's also going to be predicted by someone who's just had a private observation that he doesn't know. And these are conditionally dependent. So formally what we have here are 3 variables that stand in a Markov chain. This is the urn, this is Jonathan, this is a third person. And from Jonathan's perspective, he wants to make a report that will maximize the log ratio of the accuracy of this person's prediction and this person's prediction when they stand in a Markov chain relationship. And there's a theorem which is not published yet, derived last year, that if you have these 3 variables, and y is predicting x, z is predicting x, and there's going to be some score which sums up the accuracy of these 2 predictions, the only functions that will ensure that truth-telling maximizes expected score are plus log and minus log of the same weight. So there is a theorem on Markov structures that brings these entropies and these logs into play. That you want, honesty means you want to be predicted by someone who's statistically closer to you and unpredicted by someone who's statistically further away from you. That's the argument. Now for the second part, and I think this is now, in some sense, simpler. We're now going to try to exploit these ideas to arrive at the objectively best answer in cases where it's meaningful to speak of an objectively correct answer. And here, the work is really joint, for many years joint with Sebastian Sun, who some of you know. And there's another reason for connecting this with neuroscience. It's neuroscience. And John McCoy is a PhD student in brain and cognitive science. So everything from here on involves certainly them and other co-authors I'll mention later on. So the claim is somehow that this criterion of an answer being more popular than expected will pluck out the correct answer in some cases. And we'll start it with a trivia question, and then move on to more substantive domains. Here's a trivia question, a questionnaire, 50 states. It's 50 questions, and in each question has a very simple structure. does the largest city in this US state, is it also the state capital? Yes or no? And we're again asking people to vote yes or no and predict what the sample will vote in terms of percent. So what do you observe? You observe, first of all, that shockingly these are hard questions. In the US, on 3 different studies with MIT and Princeton students, we observe roughly slightly above chance individual answers. And more interestingly, the majority answer tends to be correct on 60 to 75% of the states. So the majority answer is wrong on a sizable portion of the states. And we want to do better than the majority answer. So the other thing about this, since we've stared at this for so many years, is that it's curious, if anyone here has lived or is from the US, some states are easy, other states are hard for reasons that are kind of mysterious. Chicago, Illinois is an example of a hard problem. Most people, the majority is reliably wrong. They think Chicago is the capital. They think Philadelphia is the capital of Pennsylvania. Neither of those are true. On the other hand, very few people think that Los Angeles is the capital of California. It's just a flaky, Hollywoody city. Cannot be the capital. Very few people think that New York is the capital of New York. Similarly, for cases where the largest city is the capital, some are easy. Des Moines, people know that Des Moines is the capital of Iowa. They don't know that Columbia, well, they do sometimes. Well, in any case. So let's take a look at one example. This is Philadelphia. What you find in this particular survey, 2/3 of the people think Philadelphia is the capital, 2 to 1. Then you ask them for their confidence. That is for the probability that Philadelphia is the capital. And you see that it's completely symmetric. People who think Philadelphia is the capital are as convinced as people who think that Philadelphia is not the capital. So confidence is not a useful discriminator. But if you ask them to predict the distribution of votes, you observe that, and this is the key panel, this is now their prediction of how the sample will vote from 0 to 100%. Those who believe that Philadelphia is the capital think that most people will agree with that. But those who presumably know that Philadelphia is not the capital predict that most other people will vote the other way. And there's an intuitive principle there that someone who is rational and voices an opinion that they fully expect to be contradicted by most people should be taken very seriously. Because if they must expect that they will be contradicted, because that means they've taken into account the information that goes into the opinions that they're about to contradict. And that's the case here in a very small, trivial way. These people expect to be in the minority, and that's why they're correct. There are obvious counterexamples which may be in your mind. What about people who believe the world will end tomorrow? We can deal with those later. Now why? What's the rational argument? So again, I will give you a very stylized argument. We're assuming now this is the model that Sebastian and John McCoy and I developed for this, assuming that people are Bayesian and they can think about possible worlds. So when they're faced with this problem of Philadelphia, they imagine there are 2 possible worlds. There's a world in which Philadelphia is the capital, which is counterfactual, and a world where it is not the capital. They don't know which is which, but they have some probability. However, they can think counterfactually and say, if Philadelphia is the capital, well, everybody would believe that. Because why would anyone disbelieve that? It's a historical city, it's the largest city. If it is the capital, who would doubt that? The vast majority represented by this red space is the fraction of people who would say, yes, it's the capital, if it was the capital. Now, what about if it's not the capital? Well, we've taken a bite out of this vote proportion. If it's not the capital, then still the majority of people would think it's the capital just because the true capital, Harrisburg, is really pretty obscure. But it's going to be a slightly smaller, and that byte there represents people who know that some other city is the capital. So in our Bayesian model, everybody knows these two possibilities. The only thing they don't know is which one is actual and which one is counterfactual. Now, we're going to ask them to predict the distribution of votes. That distribution, if you are a rational person, you're looking at this picture, and you know this is the distribution. If it is the capital, this is this distribution. If it's not the capital, and you're not sure, let's say you are 50-50, even if you're reasonably sure, that prediction for surely will be represented by a circle that's contained within this vote percentage, and that is larger than this vote percentage, because it's a mixture of those two. And we're going to count the votes and count the predictions. And what we'll observe is that the predicted number of votes for Philadelphia is this, the actual number is somewhat less. Therefore, we live in this world. We know that the world is one where Philadelphia is not the capital. And to prove that, we don't need to know whether it is or is not the capital. We just need opinions. So the claim is that, at least in a simple binary case, an answer is correct if and only if the actual percent is greater than the predicted percent. In this case, the number of votes against Philadelphia is greater than the predicted number of votes. Therefore, Philadelphia is not the capital. That's the argument, and then it becomes more complicated with more. So what do we, for trivia problems, this method just works like a charm. So it's sort of like the mouse model where you can cure cancer. We can cure people's misunderstandings of states' capitals. The harder problem is to cure people's misunderstandings of more substantive issues. But for states' capitals, the approach is almost perfect. Just to show a little bit how it works, on the left panel we are plotting. Now we're plotting individuals. This is Princeton. This is MIT. This is their actual accuracy, and this is how often they vote with a crowd. So this is how often they vote with a majority answer. This is their cultural knowledge. Do they vote with other people vote against? Turns out that there's no correlation. Now on the right panel, we plot the same x-axis, which is their objective accuracy, and the y-axis. On the x-axis, we're plotting their score, that Bayesian truth serum score that was given by that entropic formula. And this is now tallying across all 50 questions. And you see that essentially, to calculate the score, you don't need to know the right answers. But if you focus attention on the people who score very highly, they're people who are essentially getting all the states right. So it's a way of extracting the experts based on their ability to score highly using this scoring system. Now, I'm going to give you two applications just to finish up. One is really an industrial strength application, which was quite challenging. And this was a part of a competition organized by IARPA, which is the U.S., I forget the acronym, is the Intelligence Advanced Research Project Activity. And they held a tournament running over several years where the objective was to crowdsource predictions from lay individuals about events in foreign countries. And these were then aggregated by, each team had its own set of algorithms, and they were all verifiable, so they're all events that would be resolved one way or another within a time frame, a relatively short time frame. And the team that I was working with was more or less implementing this method of extraction of experts using this Bayesian truth serum score. So typical examples of the forecasting problems that were discussed. almost all dealt with foreign countries. Many of them were difficult and obscure, so a fair amount dealt with the Middle East, but we can see, well, let's say number 2, will Sudan and South Sudan sign a border security agreement before 1 December 2012? Third one, will the Vice President of Iraq's death sentence be overturned before 1 November 2012? So these are not easy things to forecast by lay people by any means. So the method then that we, and this is just a time course of number of subjects, we get about 1,000 subjects who were not experts in this field at all, but who were paid a flat rate for providing their probabilistic forecasts. So the main input was a probability that this event would actually occur or not occur. And then additionally, we asked them to input the following. So we asked them to not only provide a probability, but then say, if we randomly select 5 people who provided probability estimates, what do you think will be the lowest, average, and the highest of these estimates? So this is giving them a sense, extracting from them a sense of the distribution of how other people would answer. And then we apply the same logic. We searched for probabilities that were locally underestimated. So the idea was that the probability that's most, the best one to go with is the one that has a high local frequency that wasn't anticipated by the sample. And that criterion was compared against the criterion, the benchmark of just averaging the probabilities. So I will show you two examples of this in motion. So what you see here, each dot is an individual forecast, and the x-axis is that person's forecast. The y-axis is that person's individual score using that BTS formula. And so one way, and this is as the days go by and people are coming in, one way to create the best collective probability is simply to average on the x-axis. And typically you get something that's fairly close to 0.4, 0.5, 0.6, because there's a large spread. The other way to identify the best one is to go vertically and to go with the people who are getting high scores. And what happens if you do that is that you generally push the estimate closer to the 0, 1 endpoints, which are the extreme values. So this is another one then. So we would go, in this case, what we would do is we would go with a relatively sharp probability, assuming that these are the experts, because they are selecting probabilities that are locally concentrated and are not anticipated by the entire sample. Whereas if we inserted these people, we would get a probability that's much closer to 0.5. And that turns out to be generally a good strategy, and it improves the forecast by certainly a significant margin, but it's not infallible, as you might expect. The other example is this is now work with John McCoy and also MIT undergraduate Danielle So. A study done with MIT art, with Boston art experts on Newbury Street, asking them to examine 90 relatively obscure art paintings and estimate the market value and also indicate whether they personally like it or not. So, would anyone venture a guess between these two? Which one? The right? This is now the market value. The market value. You have a second chance. Okay, I'll give you a third chance. This is the hardest one.
No.
All right. They're both great, and they're different artists. Two more to recover. Okay, I'm going to... What do you think? Will someone speak up? Which? Left. The left is a very high quality imitation of Klimt, but not Klimt. The right is an obscure Chinese artist. And by the way, these are hard even for art experts. These are not easy. So what's the data, and does the method work? Well, we can only test the method on verifiable items. Verifiable means there has to be a right answer. We define the right answer as the market value. We're going to sort the paintings into 4 bins, A, B, C, D, corresponding to 4 logarithmic price cutoffs. D's are worth under 1,000, C's from 1,000 to 30,000, B's from 30 to 1 million, A's above 1 million. Now we asked MIT undergraduates as well the same set of questions. I'll say something about that later. They're essentially random, but the art experts are not random. When you look at the art experts' judgments, here's the salient finding. These are their ratings of the subset of paintings that are truly worth more than 1 million. And you find that the most popular category is C. The category A is chosen relatively infrequently. So in that sense, they don't seem to know much. Now I'm going to plot the same for paintings that are at the other extreme that are worth under 1,000. The yellow chart. You find again, C is the most popular rating. But they never make the mistake, that type 1 or type 2 error, whatever it is. They will never take a painting that's worth under 1 million, under 1,000, and call it a blockbuster, over 1 million masterpiece. I should say masterpiece as a evaluative judgment. I shouldn't use that. So what's happening here is that C is a safe category. If you call it a C, you can't be too far off, or a B. Well, B you can, but A is extremely risky. You know, and so is a D. You're going on the line. And the judgments are reflecting that. And these people were interviewed individually by appointment, and the RA said they were quite nervous because this is their professional competence on the line. And so you have too many C's. Everything is a C. But if you now divide by what's expected, you restore the higher proportion of A's and D's. So what you see on the right is the average score that people would get for calling, the blue line is for calling an A painting an A, and it's maximized when you call it correctly. And the same for the D's. You do best if you call it a D. And what you do essentially is you boost up the collective judgment of A's and D's. Another way to think of it is, you take a sample of professionals, and 20% of them recognize this and say this is worth more than 1 million. That is pretty much sure that it's something important, because they're just not. You don't want to count those that don't recognize it, but those that do recognize it should be counted. You don't want to count everybody the same. Now, I said I'll say something about MIT. If you want a formula for predicting the market value of art, with MIT students, we actually selected those who have never taken an art class. The best linear regression formula is what they dislike personally, plus what the experts think is valuable. That linear regression, with a heavy weight on the dislike category, is the best way to invest into the future market of unknown artists, is to show them to MIT undergraduate and say, how much do you dislike this painting? Okay, my final slide, and this is not entirely serious, but the philosophy profession has done us a service by collecting data on the secondary question. They've taken the 60 outstanding problems in philosophy, polled the profession, and to their credit got, I think, more than half of the professional philosophers to respond. Asked them to think, what is the correct judgment on these fundamental philosophical questions? I have just 2 examples here. One is aesthetic value objective or subjective? We could debate this for centuries, and probably will. And the first thing that was asked is, how do you feel about this? Is it subjective? Is it objective? Or is there some other answer? And then you as a philosopher were asked to predict what you thought your peers, how your peers would vote. And that's the meta-prediction column. And you see some interesting discrepancies, and if you believe everything I've told you up to this point, then we have resolved some basic questions in philosophy, starting with aesthetic value is objective, because the number of actual adherents exceeds the number of predicted adherents. And the other one, which should disturb you even more, is that the mind is non-physical, because the number of philosophers who believe that is greater than they're closet non-physicalists in the philosophy profession. The 27 who think it's non-physical, and they think only 24% are, and some are shy about it. Now, I really can't claim that, and I don't believe it, but it shows that the approach, once launched, can go dangerously far. I should just say my co-authors, just to acknowledge, starting with Sebastian and John, and George Lowenstein, not to be confused with Jonathan, although people have asked me, why is George doing this computational stuff? I have no idea. And a large collective team on IARPA, including done on several projects and a study that I didn't mention on skin lesions. Thank you very much. Question?
So the whole thing is doing some sort of crowdsourcing tool.
Yes.
I mean, that most people are rational.
All the theorems require that everybody is rational.
And how true is it?
How true is this? It's not true. The greatest thing of mystery is that people are directionally Bayesian when they ask me from their opinion. But if you put them in the situation that I did with these things, when they draw one chip, they're generally not Bayesian at that point. They're Bayesian in a real world situation, but not Bayesian in the stylized drawing chips from urns, which is very embarrassing for Bayesian. If they draw 2 or 3 or 4 chips, then they start to update. But that first chip, well, little experimental evidence is that first chip is not treated as information. And Robin Dawes, there is a whole literature in psychology called consensus effect, which established this phenomenon that people's opinion influences their prediction and treated as an error in judgment. And Robin Dawes, 1980, said this is not an error in judgment, people are being good Bayesians. And he claimed that the reason psychologists ignored this is because they didn't treat a single data point as sample as informative. So we don't really know why people are qualitatively, they're very strongly Bayesian qualitatively. On those trivia questions with state capitals, the people believe the answer is yes. Given it, predict about 30-40% greater estimate than people believe the answer is no. So all of those assumptions hold. Okay, but I know they're not Bayesian. They're certainly not consciously Bayesian.
It was probably something that I really did not understand, so I will ask him this way. I have 2 sheets of paper, one is black and one is white. And I asked the subject to tell me which is white and which is black. Then the prediction and the actual result are identical, because no one will say that the black is white. So where is the theorem that you said that the prediction must be, it can never be, the observation can never be beyond the prediction. It can be the same.
So this is a case where we have we have a sheet on the table that's black. We ask everybody the color. Everybody says that's black, and everybody predicts it's black. So that is a case where there's no private signal. Everything is common knowledge, and in fact, technically, that's excluded from the assumption.
So this is like the zero, which is not defined.
You need
out of the
yes. there was a point where I went very fast over some slides. You have to accept that your personal signal is informative about the distribution in epsilon. If your personal signal is completely uninformative, then the intent is severe. So it has to be, this is something that's called stochastic relevance. Your private information has to be relevant. It doesn't have to be strongly relevant, but it has to be.
So if public information drops to zero, then the field doesn't...
Then the incentives disappear. Then there are no incentives. The equilibrium is unique also with the proviso that if everybody lies systematically, like everybody who sees yellow says blue, everybody who says blue says red, everybody who says red says yellow, that's also an equilibrium. This is remapping works just as fine. But apart from that, it's unique. Strict equilibrium is unique.
I have two questions. One, have you tried to apply it to the stock market?
That's it.
I mean, if you can make good predictions, then it should be very big chance.
Rational.
Not in any... the answer is no, and I'm actually pessimistic because I think the amount of common knowledge is very high. But a natural application that was never done would be to have a group of investors do this regularly, daily, predict what's going to happen tomorrow, predict what their colleagues will say, and then you see if it works. That experiment is never done.
And second question, if I believe that the world will end tomorrow, that's what you started with.
Yes.
And I know that other people don't share this point of view, then I'm probably right. That would be...
Yeah. This is the crazy set objection. So, there's an important objection, important substantive objection. If you believe that the crazy sect knows all scientific evidence that you know and still believes, then they're worth listening to. But if they don't know something that you know or they believe something that's false, then they're not. That was my timer for stopping. Do we believe that the crazy sect individuals are Bayesians and they are scientists? It's actually not so easy to answer that question because take something like global warming. I've been on a panel and there was some discussion and someone said, what we need is more information, more science. And one of the panel members said, the people who deny global warming are actually the best informed often. They know all the scientific evidence except they can deal with it. So knowing scientific evidence doesn't really nail down your opinion. I think that the natural way to interpret the crazy sect thing is that they have received a signal which is incorrect. They have received a signal that the world is going to end. And it happens to be a false signal, which happens sometimes. So the issue is, it's like someone who gets a stock tip, but the stock tip is false. As a matter of policy, you should go with your stock tips, on average. But occasionally, you will have additional information that other people don't, and precisely that information will mislead you. It certainly happens. Let's have a court, and someone runs into a court case and says, we've done this test, DNA test, to prove that this person did it. You want to take that into account, but if that test is misleading, it will make you go the wrong way. So all the theorem says is that more information is good. People who know that they'll be in the minority have more information. And sometimes more information will actually give you the wrong answer. That's just the way life is.
One more. Sure.
Okay. You should also take into account that there might be hope or reward for for example, telling the truth in church.
So this is where people actually have a stake in the answer. or stake in the aggregate outcome, something like that. Technically, no. There are easy, not very elegant ways of dealing with that by saying that score is just going to be translated into financial incentives, and we can make those incentives so large that they overwhelm any personal interest you might have in being honest or in distorting your answer. So for instance, if I were asking you a sensitive question on heterosexual practices, the answer I would give is, well, if the score is going to be a few dollars, that's not going to be worth it.
I'm not sure what you said.
Let me repeat that. Thank you, Jerry. But if something is so extremely sensitive, then making the incentives very high, I don't know if it's going to work. So I think this is mostly interesting for situations where people don't have a very strong internal reason to receive.
Good question. So assuming that the world will not end tomorrow, something that I don't believe in, but still it could happen, then we'll have another talk on Thursday as part of our regular